This is Ryan Peterson from Cornell University. He's a student there. He works with Gun Sirer, who is a grad student colleague of mine and is now on the faculty at Cornell, and he's going to tell us about basically a distributed publish and subscribe algorithm that he's been working on in System.
Thank you, Jeff. So, can everyone hear me? No. Oh, okay. Now you can hear me. All right. So I hear that Google occasionally visits news sites to collect information and even crawls the web sometimes. I'm going to talk about a related problem to this that I've been working on at Cornell for the past year. This is joint work with Rama down the street at MSR now and Gun Sirer at Cornell. So one of the reasons that crawling the web is so difficult is because the web is big and it's getting bigger. There's your words of wisdom for the day. They're including an increasing number of frequently changing data sources, such as web pages that can change multiple times a day, the sensor networks that the future promises, and extensive online databases that clients want to know when there are updates posted to these. So continuously monitoring these are important to clients who have some specific data, some specific content server that they want data from, and they want an efficient way to get that data. So the current way to accomplish this is using a standard called RSS. But as you'll see, RSS has some problems. So on the left here, we have clients, and on the right side, we have content servers that presumably have content that the clients are interested in. So the way RSS works is that if a client's interested in some content, it pulls that source of content directly. If there are multiple clients, they all pull it independently. They don't share updates with each other. This is a real problem. Here's why. As you see here, if you have multiple clients all pulling for the same data, they all pull independently. This causes a problem at the content servers. They see way too much load, more than they can handle, and so they've had to impose bandwidth limits. In other words, Slashdot, for example, doesn't allow a single client from pulling more than twice an hour. This places a problem at the client side. If they pull every half an hour, they can't detect updates better than 15 minutes on average. So we decided to build a publish-subscribe system for the web that can efficiently get content from content servers to the clients who are interested in it. We call this system Corona, and it decouples the clients from the content servers, allowing the clients to communicate with this cloud in the middle by sending in subscriptions, and the cloud will then pull the content servers in an efficient manner. So as I said, this is a publish-subscribe system. In particular, it's a publish-subscribe system that interfaces with the existing web. Many publish-subscribe systems have failed or have even been unable to be deployed because there's a requirement on them that the content servers must push the data to the clients. In other words, it's not compatible with the pull-based architecture of the web. So it's important that this is backwards compatible with the web. This cloud in the middle achieves an efficient polling of the content servers by using an optimization framework that's under the covers here, and I'll explain that later in the talk. But this provides a way to most efficiently pull the content servers for the data we're interested in. Near the end of the talk, I'll talk about the implementation of this system as well as how well it performs and a wide-scale deployment. So our main focus here is what's inside this cloud. How can we make it efficiently pull the content servers? So we have several underlying properties or goals that we want it to have. First of all, it has to be scalable. We have an increasing number of clients. We have an increasing number of nodes in our system that is only growing as the number of subscriptions increases. And so it should be able to tolerate large workloads, larger than we can foresee right now. Second, we want it to be robust. This system should be able to tolerate multiple failures without degrading the performance in the system. And lastly, we need it to be distributed. This system should be distributed because it's inconceivable that any one node in the system could possibly pull on behalf of all the clients and all the subscriptions in the system. This is especially true because of what I said about the content servers. They've imposed a bandwidth limit. There's no way for a single channel to even, or a single node to even pull for a single channel because it would only be able to pull every half an hour or so. So we have a distributed network here, each node pulling on behalf of the clients. And in order to provide some of the guarantees, some of the underlying properties that we would like our system to have, we organize it as a structured overlay network. This provides some guarantees that I'll talk about later, and it also sets up our problem of choosing which nodes pull each channel in our system. So intuitively, we want more nodes to pull channels that are more popular and fewer nodes to pull channels that are less popular. This depicts a concept called cooperative polling. What this means is that the nodes all pulling one channel are sharing updates with each other so that they can detect the updates more quickly. In particular, we frame this problem as a resource allocation problem. We want for each channel to choose which nodes pull for the channel and how many nodes pull for the channel. Those are the two important key factors here. So how do we do this? Well, one way we could do this is to introduce some heuristics. And there's some pretty intuitive ones. For example, what if for each channel in the system, we pulled it with a number of nodes proportional to the number of subscriptions for that channel? There's some channel with 50 subscriptions should be pulled with twice as many nodes as a channel with 25 subscriptions. This makes sense, but I'll show that there's a better way to do this. Instead of relying on heuristics in order to get the performance we want, let's frame this mathematically, and so we can achieve the optimal number of nodes pulling for each channel in order to most effectively make use of our resources. So the mathematical optimization relies on coming up with fundamental trade-offs in our system. And as I'll show you, there's a fundamental cost to pulling these nodes and a fundamental performance trade-off. We want to be able to detect updates as quickly as possible using as little bandwidth or as few pulls to the content servers as possible. In order to set this up, we need some efficient way of optimally choosing these nodes, and we need it to adapt to the system. As the number of subscriptions changes, our system should constantly be reorganizing itself, changing which nodes are pulling which channels in order to keep the performance as high as possible. So in order to do this, we need to set several performance goals. These performance goals allow us to say what we want our system to achieve in a very formal mathematical way. Corona is a general enough framework that we can come up with any number of performance goals, and I'll show you a couple that we've implemented in our publish-subscribe system for the web. So one such goal is called Corona Lite. In this case, we set up the optimization as follows. We want to detect updates as quickly as possible. Averaged over all the subscriptions, we should make the delay between the contents changing and the clients detecting that change as fast as possible, such that we don't go over a certain network bound. Say, for example, we don't want to impose any more load on content servers than they currently see through RSS, or perhaps the network has a certain amount of bandwidth available to it. System designers should be able to choose that value in order to customize their system. On the flip side of this, suppose that we want to know that we'll detect updates on average only 30 seconds after they're updated, for example, some set time value. To do this, we can set up the optimization problem by minimizing the total amount of bandwidth that the system uses, while guaranteeing that the average subscription detects updates in a certain amount of time. Later in the talk, I'll introduce another optimization goal that we've set called Corona Fair. I'll bring that up again in the evaluation section. So in order to achieve these performance goals, we take advantage of certain properties of our underlying structured overlay. So here's our structured overlay with each of the machines in our system. And they're organized in a logical ring structure. The logical ring structure is a circular identifier space, and each node has some identifier here. Now remember, our goal here is to choose how many nodes are pulling each channel. In order to do that, we need some way of formally and uniquely identifying clusters or groups of nodes that will perform this cooperative polling for a channel, as I've talked about. So to formally come up with these clusters, we introduce a notion called polling wedges. So suppose that some new subscription or new channel enters our system, and it gets randomly hashed to this red node here with code with identifier 2200. That's called the home node for the channel, and for the time being, it'll be the only node polling for this channel. However, if this node somehow decides that there should be more nodes polling for it, it can increase the polling wedge of the cooperatively polling nodes by assigning nodes surrounding it with a common prefix to pull as well. So in this case, we define a level 1 polling wedge as all the nodes that share the first 3 hex digits with our home node. Likewise, if we want to increase the number again, we can go to a level 2 polling wedge and make the prefix slightly shorter. So notice that since we're doing this based on prefixes, every time we increase the level by 1, we're increasing the number of nodes pulling by an exponential number. It's growing exponentially since we're matching a bigger and bigger prefix, or smaller and smaller prefix. And once we define what our pulling wedge is, it's exactly those nodes that can be uniquely identified that pull the content server. So why did we do this? Why did we come up with this pulling wedge concept? So as I said, we want to find how many nodes to pull each channel. One way we could conceivably do this is for every channel, choose a value between 1 and n, where n is the number of nodes in our network, and choose exactly those, fine-grained control of exactly how many nodes are pulling each channel. But this is a huge problem. It's difficult to choose a value between 1 and n for every channel so as to optimize our performance goal. And so by introducing these pulling levels, we've reduced the problem complexity from n, choosing between all the nodes, to just log n, choosing the size of our pulling wedge, where a pulling wedge of 0, again, is just the home node, and a pulling wedge of log n, level log n, would be all the nodes in the system pulling. So now that we've set up this convenient concept of pulling wedges, we can more easily model our optimization mathematically. So as we see here, the number of nodes pulling we can compute as b to the L, where again, L is the pulling level in our system, and b is just the base of the underlying structured overlay. And now we can calculate both the performance and cost of our system. Here we have the update detection time as our performance, and we have the bandwidth cost, or how much data we're pulling in total from all the content servers. With these two, we can set up, this is just an example optimization problem we can set up that uses this. Here we're minimizing the performance, or minimizing the update detection time, while guaranteeing that we don't use any more than we're minimizing the total load on the network while guaranteeing that we detect updates in at least, or at most, time t. Okay. So I'm only going to give a high-level description of how this optimization part works. I refer you to our paper in order to get the more mathematical details. But in order to cover all of the math in this would require a longer talk. But I do want to give a high-level description by saying that once we have this general optimization problem, we recognize that it's NP hard because we need to choose an integral value for each of the levels in the system. This reduces from solving the multiple choice knapsack problem, which we know to be NP complete. However, we've come up with a fast, efficient optimization approximation algorithm for this optimization that runs in time MD log MD. We do this by taking our optimization problem and transforming it using Lagrange multipliers into a single expression that needs to either be maximized or minimized. In doing so, we introduce one new variable, lambda. But notice that for a fixed lambda, we have m independent equations, one for each channel in the system, that can be minimized independently. So we need to choose a value of lambda, and we do this by first recognizing that there are a finite number of lambda values that could possibly affect the solution, and we can pre-compute and sort these values of lambda, and then use standard bracketing algorithm techniques to zero in on our value of lambda, and then independently maximize or minimize the other equations or expressions. So the takeaway here is that this is fast and simple, and it's near optimal. We've shown that this algorithm comes within one channel per node of the optimal solution. So by running this periodically, we can adapt to changing workloads in our system. So the question is, how do we do this in a decentralized manner? So far, I've given you this optimization problem and assumed that we just have global knowledge about the whole system. But as I said, it's a decentralized system. Each node here cannot talk to a centralized authority because introducing a centralized authority would bring down the robustness requirement. We don't want a single node failure to bring down the system. Instead, so what we have here are three questions that you should be asking yourself as it relates to this decentralization. How do we achieve this optimization algorithm in this decentralized manner? Once we've chosen the nodes that are pulling each channel, how do we assign the pulling level to that channel once we know the level that we want? And when a node detects an update, how is that update propagated among the nodes that are pulling for the channel? So starting at the top, how do we solve the optimization problem in a decentralized manner? Well, one thing we could do is propagate information between all of the n nodes so that each node has a complete view of the network. In other words, each node knows some subset of the channels in the system, and we could have the other nodes pass all the information that they have about all of their channels. However, this is highly inefficient. Passing every single piece of information that every node knows to every other node is going to be too time-consuming and bandwidth-intensive to do here. So instead, we have nodes approximate trade-offs based on their non-local channels. It knows about its own channels, but we're going to have nodes aggregate coarse-grained information about the other nodes, about the other channels in the system, and send those to the other nodes. So in particular, this curve here represents the performance by cost on the left-hand side, and all the channels in this whole system sorted by popularity across the bottom. So if each node knew this curve perfectly, then it would know where its channels fall in this curve, and it would be able to solve the optimization problem locally based on what it knows about this curve. However, each node only knows about its own channels initially. In other words, it has a few sparse points on this graph. So what we do is we split the normalized performance versus cost on the left into a number of constant-sized buckets. And each node looks at the channels it has in each of these buckets and aggregates the information about those channels into one cluster. So one cluster would represent one bucket on this P over C. And using these clusters, each node can then come up with has a close enough approximation of the global view of the system in order to run the optimization algorithm locally. So once we have these clusters, we need to disseminate them to all the nodes in the network. How do we do this? We rely on the underlying structure of the overlay network. In other words, each node can route to any other node in log time. That's one of our requirements of the underlying system. And so if you imagine at each home node a tree rooted at that node, we essentially propagate these clusters that the nodes have come up with up to the home nodes. And so eventually, by each node passing the clusters to their one-hop neighbors, every node has an approximate view of the system. At this point, each node runs the optimization algorithm locally based on what it knows and uses the same underlying hierarchy in order to disseminate the polling levels that the nodes decide to define the polling wedges. Now, you may notice that it's possible that two different nodes, since every node is polling here, or every node here is running the optimization algorithm locally, that they may disagree at some points. There may be two nodes that, both looking at the same channel, one decides it should be at polling level 3 and another decides it should be at polling level 4. But that's okay. At worst, the polling wedge will be one size too big or one size too small, and in a few minutes, the system will stabilize. So it's okay if one wedge pulls too many times in a short 3-4 minute period of time. So once a node detects an update, we need to get that update both to the client and to the other nodes polling for this channel. Again, we can use the same underlying structure of the overlay. If a node detects an update, it can strip away all the old stuff in that update and just leave the new piece of information, because all the other nodes presumably know what has been seen already. And then it can pass that new information to the home node, which can then disseminate it to the other polling nodes in this wedge. And likewise, the node detecting the update can somehow send a message back to the client. So I've described how the system works under the hood, but I haven't talked at all about the implementation of the system, how we actually built it, and some of the problems we ran into. So we layered this on top of Pastry, which is just a structured overlay. It's out of Rice University. And we've set it up so that it monitors RSS feeds and Atom feeds, as well as detecting changes on web pages. We do this using a difference engine, which is a small module that we build that can compare the old polling results to the new polling results in order to check for data in our specific application. For the front end of our system, we use an instant message protocol in order to quickly send the updates to the users who are interested. So I'm going to talk in more detail about this difference engine and how it can be customized for different applications. System designers can build these and plug them into the system in order to pull different kinds of data. For example, if some researchers want to design one of these for a sensor network, they could design a difference engine that knows how to read the data out of those sensors. We've built two specific difference engines, one for news feeds, RSS and Atom feeds, and another for detecting changes in generic HTML pages. I talked about this front-end system just a tiny bit. Let me introduce that. First, notice that all we've talked about here is what's inside this cloud, the polling nodes for the content servers. We call this cloud in the content servers the back end of our system. We introduce an instant message front end to this system, which is actually what communicates with the clients. I'll call this the instant message gateway, but just think of it as a machine that connects to all the instant message protocols we use, currently AOL Instant Messenger, Yahoo Instant Messenger, and MSN Messenger. The clients can send just regular instant messages to this IM gateway, and the IM gateway can then forward these to the Corona Cloud, to any node in the Corona Cloud, and the Corona Cloud knows how to handle it. Then when the Corona Cloud detects a change, any of the nodes detects a change, it can again make this just encapsulate just the change to the content and send it back to the instant message gateway, our AIM box, let's say. That box can then send the new information to the clients in just instant message format. We've decided to pull this instant message gateway out because of limitations that existing instant message systems place on our system. In particular, they don't allow us to log in from many points of presence at the same time. So ideally, we'd like to log in from every node in our system into the same screen name. Then any node, when it detects an update, could immediately send that update to the clients. However, since we can only log into one place, and instant message services generally only allow a single user to send a certain number of messages per amount of time, we've pulled this out into this gateway that handles all of this for us. So our backend still operates exactly as before, detecting updates according to our optimization engine. And the IM gateway is just the front end that could easily be replicated in order to provide more robustness or fault tolerance. So by having clients interact with our system using this instant message front end, we make it very easy for them to adopt the system. They don't need to learn any new software in order to use this, because most people are already familiar with how to use instant messages. So by sending a single message, they can subscribe to any website or feed they want. And they receive updates while they're working. If this becomes bothersome during work, if you're getting too many IMs, you can use different features to restrict this. You can put it in digest mode. You could ignore certain channels for a certain amount of time. And things like this, just to give you finer grained control over how the system's acting for you. So in particular, the most important benefit of using an instant message front end is that we have push-based notification. While we can't change the content servers and ask them to push updates to our system, we can, once we find these updates, push them directly to the clients. This relieves the clients from having to poll, such as an RSS, and allows them to just sit there and the updates will come to them. As I mentioned, this is easy to adopt. And as an added side effect bonus, we get front-end authentication. Users have to log into their favorite instant message services in order to use it. And by logging in, they're guaranteeing that they can only see the channels that they have subscribed to and receive the updates for those channels. So we've built this system, and I want to show you how it performs in the wild. So first of all, we recognize that since we're comparing this to RSS, we could not find any RSS trace studies in order to form as a basis for our comparison. And so we did a trace study at Cornell between the gateway between the computer science department and the rest of the university for a period of time and just collected statistics. And then also at a wider scale, we tracked a bunch of polls at syndic8.com, lists a bunch of RSS feeds that we've been able to track in order to learn how they update and how users interact with them. We've also tested our system against this foundation, both in simulation at a very large scale and using PlanetLab in order to do a wide area deployment of it and see how it works in practice. So in looking at this in simulation mode, the large-scale the large-scale deployment with a lot of nodes, we see that on the left we have the update detection time, how quickly we're seeing the updates. And across the bottom we just have the time of our 6-hour experiment. And we see that legacy RSS has a constant update detection time. Each node is polling periodically and getting updates every 15 minutes on average. However, notice that Corona Light is performing much better than this. Remember that Corona Light is the performance goal where we want to use the same amount of bandwidth, but maximize our performance. In other words, detect the updates as quickly as possible. So we see here that we gain more than an order of magnitude, and we do even better with Corona Fast, where we set an update detection time of 30 seconds in this case. So it's not surprising that that does level off at 30 seconds. And it also isn't surprising that we're able to get this update detection time this low. After all, getting update detection time is just as simple as making, for example, every node poll every channel. But the real beauty here is that we're not doing that. We are efficiently choosing which node should poll so that we don't increase the bandwidth of our system. So here, RSS uses a constant bandwidth, but that same Corona Light, which achieved more than a magnitude of order faster updates, is using no more bandwidth than RSS across the system. Corona Fast is using slightly more bandwidth, but with this mere increase of about 20% bandwidth, we are achieving a much faster update detection time, our target of 30 seconds. And on the left here, you see 2 spikes, and those are just the amount of time it takes the system under this deployment to stabilize in order to propagate these clusters and run the optimization algorithm. And again, this could be tweaked by having the system designer choose how quickly these propagation values move around the system. So I talked briefly about using heuristics in order to solve this same problem. We have this resource allocation, choosing a number of nodes for each channel. So again, we have legacy RSS on the left, 900 seconds, 15 minutes on average update time. And now suppose that we did use this proportional heuristic that I mentioned. We have a number of nodes polling proportional to the number of subscriptions for the channel. Here we see that we do indeed perform much better, almost 3 times better than just regular RSS. And we achieve even better by using the square root metric. Instead of polling with the number of nodes proportional to the number of subscriptions, we poll with the number of nodes proportional to the square root of the number of subscriptions. Introducing a square root in this fashion is a common thing to do when you're trying to maximize things like this using heuristics. But in this case, we see that Corona Light performs much better than, obviously, legacy RSS, but also than the 2 heuristics that I talked about. And Corona Fast performs even better, albeit with slightly more bandwidth, about 20% as you saw. But Corona Light uses the same amount of bandwidth on the left, but performs much better. So the question is it possible to design heuristics that perform as well as Corona Light? It could be. We could sit here and come up with some heuristics and try them out and test them and see if we can get that bar a little lower. But the problem is that heuristics don't provide any guarantees on how well this is going to work. And indeed, when the workload in the system changes, if the number of subscriptions increase or the distribution of the subscriptions over the channels drastically changes, we might have to sit at the drawing board again and design a new heuristic. Whereas with Corona, we've designed one optimization that we know we want our system to achieve, and it propagates the values within the nodes and does it on its own. So now let's look at a slightly different view of our channels and our update detection times in the system. Instead of looking at an average of all of the nodes, of all the channels in the system, let's look at each one individually. So here we again have update detection time on the left, again a log scale. And across the bottom we have each channel in the system sorted by how quickly that channel updates on the content server. So how like a news site might update more quickly than a blog, for example. Here we see that there's a cluster of nodes, or a cluster of channels rather, that are updated very frequently. The content server are constantly changing, and yet we're not detecting the updates that quickly. Depending on the application, this might not be desirable. And so we could go to the drawing board and come up with another just optimization algorithm that would help achieve something better in a particular application where we want to quickly find updates in a channel that's constantly changing. So I've already introduced 2 performance goals that I've talked about in the previous experiments. We introduced another one called Corona Fair. By taking into account the update interval of the channels, as well as the update detection time, we come up with a different optimization problem that favors those channels that are updated more frequently. Using this Corona Fair metric, by introducing this new performance goal, I hope I've convinced you that we can just come up with new optimizations and just plug them into the system, and the system will know what to do with them. Looking at this back at the same graph we just looked at before, we add some blue nodes, which are the update detection times of the channels once we've employed this Corona Fair goal. And in this case, we see that we have increased the performance of those channels that are updated frequently at the cost of detecting updates a little more slowly on the nodes that aren't updated as often. So the system designer can design their own optimizations based on what their applications, what the clients want and what the application is used for. So in addition to doing these simulations on a large scale, we've also done a wide-scale deployment on PlanetLab. PlanetLab is a distributed testbed over the internet that allows researchers to deploy services at a large scale and experiment with them in more realistic settings. As you see here, we have a significant number of clients. We're building up steam, and I think you should watch out because we might be cutting into your revenue soon. Let's take a look at what PlanetLab is doing with its wide-scale deployment. Again, we look at the same Corona Light metric, trying to optimize the performance. And we see that we have indeed increased the update performance by more than an order of magnitude. This is over about 7,500 real channels with a natural distribution of subscriptions on those channels totaling 150,000 subscriptions. And again, we have not gone over the load imposed by legacy RSS because that's the bandwidth limit that we set. We don't want content providers to see any more load than they already do. So we've shown you that we have this high-performance system that we've actually deployed on the web, backwards compatible with the web, and people are currently using it in order to detect updates to their favorite sites. I've also shown you that it's easy to create these optimization functions based on the application, and I've shown you 3 in particular. So the system overall was practical and efficient to deploy at a large scale. So there's some future directions we want to take this, and if any of you have any insights on this, I'd be happy to talk to you afterwards. One particular direction is looking at content-based publish-subscribe systems. So far we've been looking at a topic-based subscriptions. In other words, each user subscribes to a specific feed or a specific web page, and whatever appears on that web page is sent to the client. But for some systems, it would be useful to be able to subscribe by keyword. For example, looking for any occurrence of volcanoes or maybe earthquakes in this area over all the news sites and getting instant messages when it finds those. In addition, we've been talking to the database group at Cornell about adding support for this and predicates to a keyword-based subscription service, where we could say things like, when my favorite stock increases by more than 5% a day, I want to be alerted. So by allowing clients to come up with more complicated queries, it gives them more control over the updates that they receive. Another thing related to this problem that we want to look at can be expressed by taking away the clients of our system and adding some legs and eyes to our cloud. You obviously all recognize this as a web crawler. The problem here is very similar. We want to, again, pull the content servers in the most efficient way possible in order to keep, for example, a web cache fresh. So here, given a set of pages, we continuously crawl these pages. It's the type of web crawler we're designing here, and catch the changes in the system as quickly as possible. This problem is essentially the same. The only difference here is that we're looking at a different goal or a different system that we want to optimize. Instead of trying to get updates to clients as quickly as possible, we want to detect changes and put them perhaps in a web cache. So we need to create a new freshness metric, and that would be the first step towards achieving this goal. After we come up with this, again, we have a choice of what we do with it. We have a metric, and we can maximize that metric while constraining bandwidth, like before. That's similar to coronal light. Or minimize the bandwidth that we use in order to achieve some set performance in our cache. For example, depending on how we structure the freshness metric, maybe we want it to be 75% fresh, whatever that means. But the point here is not that we have a specific metric, but that by coming up with a metric, we can plug it into the system and have it stabilize on that optimization. So some past work by Jungho Chu and Hector Garcia Molina have looked at how to optimally poll web caches in order to optimize some metric. The way they have two metrics, freshness and age, and I'm not going to go in detail what these are, but our work is different in a number of ways. First of all, their freshness metric is such that pages that update too frequently are not polled at all. This may be undesirable for some applications. You might want to guarantee that everything in your cache is at most a certain age. So they've analyzed these two metrics and come up with a closed form expression for polling based on these. But the point of Corona is that we have a general framework where we could plug in these two metrics or come up with more, and without analyzing them mathematically, plug them into the system and see how well they perform for our application. Also, Corona is a distributed system, so it can scale to larger sizes than simply being handed a closed form expression that you would have to use in a centralized fashion. There's also been a lot of related work on publish-subscribe systems. Again, I've talked about topic-based versus content-based systems, whether we use keywords or just subscribe to specific data sources. And again, Corona is a topic-based system, but differs from previous work in that it uses this optimal fundamental trade-off between the resources in the system in order to achieve a goal. There are many peer-to-peer overlay networks, so we've built ours on top of Pastry, but there are plenty of other ones that provide similar guarantees. The only guarantee that Corona needs is that the underlying network supports log time hopping, log time number of hops from one node to another in the underlying network. And so it could be built on top of these other networks, and it would work just the same. And lastly, there have been other micronews dissemination projects. In particular, Feedtree, for example, also uses this cooperative polling technique in order to detect updates more efficiently. But it creates a tree over the clients based on heuristics. And using these heuristics, the clients know about their neighbors and can forward the updates to the clients through this tree. Again, we've chosen not to rely on heuristics as we believe it provides better performance in a general sense. So in conclusion, we have a new approach that we've introduced for building systems, using fundamental trade-offs between resources and coming up with optimization problems. And we've shown you that we have an approximation algorithm that for a wide range of these optimization problems, we can achieve near optimal performance quickly and stabilize with changing workloads. I've also shown you an example prototype application that we've ran simulations on and even deployed in a large scale that exemplifies this systems approach in practice. So overall, I believe that instead of relying on heuristics as systems become larger and more complex, it's important to look at some of these fundamental trade-offs in the system and decide how we can best take advantage of, for example, the cost and performance in order to guarantee that our systems are behaving most efficiently, even as our systems become much larger than they are today. And thank you. With that, I'll take questions. Yes?
So I'm interested in the false positive rate you have in the different engines. So how frequently do you find that it response changes to change?
When they really haven't? Right. So the two difference engines we've built do not deal with this because we're looking at feeds in particular. We designed this originally as an RSS publish-subscribe system that performs better than legacy RSS. And so we look at RSS feeds which have a very specific format. And by studying, or just by looking for the new headlines in this format which the publishers place there, we know which ones are new. And when we detect web pages right now, we're just looking for changes, and we're not looking for things that the client might necessarily be interested on that web page. But the idea is that it's general enough that someone could build a difference engine using any number of techniques that detects what they want from the data sources. Yeah.
So looking back to your third method, you had a very apparent step on the update rate.
The third.
Your third method.
Okay. Right. Like this.
Right there, a very obvious step on. So you want the whole entire order of magnitude for 3,000 range.
Mm-hmm.
Is there any explanation for that? Why it's so obvious?
Yeah. The explanation here would have to be that since we're dealing with these exponentially growing polling wedges, as we increase the polling level, the polling wedge has exponentially more nodes in it. That in this case, it must be that because of our distribution of subscriptions, we have some nodes that fall in a polling wedge of some size and some nodes that fall in a polling wedge of the next size. And in this case, those updates are being detected. Well, that would be twice as fast. Let's see.
So it's not a factor of 16 there, you're saying?
Right. So.
You could have a wider granularity polling wedge.
Right. So I mean, one solution to this would be, for example, if, like I said, it would be very nice if for each channel we could choose exactly how many nodes are pulling that channel. You know, an integer between 1 and n. Whereas we're using an exponential polling wedge. So I'd be happy to hear any techniques that you might have for increasing the granularity of our optimization algorithm. A bit pattern on the mask.
The original slide had a base 16 hexadecimal number. Are you just using a pure matching on the top hexadecimal?
Yeah, we are just looking at the prefix of that. And that was just an example. We're not, our identifiers are longer and we're using different size prefixes. But the idea is that we are just using the prefixes of this in order to choose which nodes are pulling. All right, thank you.